Alright, so let's start thinking a bit more about inductive logic. Remember last time I said, we figured out how we can figure out the probability of not A given the probability that A, right? But we still need to figure out, the probability of A and B, even if we know the probability that A and the probability that B, right? And the probability that A or B, right? And I said, ended last lecture with saying, well, think about it. What's going to be more probable? Probability that A is true, that A and B is true, or that A or B is true. Now there's a little bit of a trick question because there's one circumstance where they can all be equally probable, but if they're not equally probable, they have to have a certain order. Well, what's that order going to be? Some of you guys might have guessed, I said look at the truth table when we're talking about deductive logic, and it'll probably clue you in, right? It's a lot easier, even in deductive logic, for A or B to be true than A and B, right? It's also easier for A or B to be true than just A to be true, right? A and B is only true when both are true. A or B is true when either is true. A is only true when A is true, right? Look. I think a little bit of a graphic representation will help here. Your book calls these Euler diagrams, there's sometimes hear them called Venn diagrams. There's actually a distinction between Venn and Euler diagrams. Some of these are Venn diagrams, some of them are Euler diagrams. If you take a math class, they might get mad at me, because I didn't go over this distinction. For our purposes, I really don't care. It's really not important. Just circle diagrams, Venn diagrams, Euler diagrams, whatever you want to call these. I think just to help, this visual representation will help a bit with these, right? Now, treat A and B as any propositions you want, right? Any propositions you want that overlap, right? Could be, it's cloudy tomorrow and I ate oatmeal for breakfast, or it's cloudy tomorrow and it's cold, or I watch the Great British Baking Show with dinner and go to sleep before 10 o'clock, right? Plug in whatever you want for A and B here, Circle A is just all the circumstances where whatever statement A is comes out to be true. Circle B is just all the circumstances where proposition B, statement B, whatever it is, turns out to be true. Where they overlap is where both of them are, right? Well, now look. A and B is the overlap between these two circles, right? When you say A and B, before you said A and B, you had this A circle, you had this B circle. Once you say A and B, you have narrowed yourself down to just this little sliver of both, right? Well, we're not even talking about probabilities, but look, obviously, the A and B section, the little section where both of these are true, is way smaller than either of our circles. A and B is obviously much smaller than A. So A and B is going to be less likely than either A or B. And that's the usual circumstance, right? When you slap a B on it, whatever it is, A and B usually comes out to be less likely than either of its parts. There's an exception to this I'll talk about in a second, but this is the usual thing, right? A or B, well, this whole space, all the space that's taken up by A and all the space that's taken up by B is A or B. Obviously, this is bigger than A, so A or B will have more chance of being true than A. Probability that A or B is usually greater than A. So now given all this, how would you order the probability that A or B, probability A and B? Now look. Probability A or B cannot be less likely than probability that A. It is either the same or greater. Probability that A and B cannot be less likely than probability that A. It's either the same or less. Now, these can all be the same probability. Probability that A, probability A or B, and probability A and B could all be equal. Well, there's one circumstance where that's true, and that's just when A swallows up B entirely, right? In that case, all three have the same probability. They're all in the same order, but barring this weird circumstance, they're going to get probability that A or B more likely than probability that A, probability that A and B less likely than A, also less likely than probability that A or B. All right, so we have an ordering of these, and you guys can probably see why the question on the logic quiz that you got wrong, or some of you got wrong, was wrong. You know, we're tacking ands on about this woman being I forget what exactly details about her life. When you tack those ands on, with each and, it gets less likely. Or at least, at the very least, it gets no more likely and tends to get less likely. Well, okay. How exactly do we figure out the probabilities, though, of A and B and probabilities of A or B? We know this is usually less likely to be true, this probability A and B, than A, but what exactly is the probability? We know that this A or B is usually less likely to be true than A, but what exactly is it? Let's start to get into this. The first thing to talk about is the multiplication rule. If A and B are independent, and remember this idea of independence we talked about a lot last lecture. Independence means that A being true tells you nothing about whether B is true and vice versa, right? If you know that A is true, you don't know whether, it doesn't make B any more or less likely. That's what independence means. If A and B are independent, but only if A and B are independent, then the probability that A and B equals the probability that A times the probability that B. But only if A and B are independent. Only if the truth of A tells you nothing about how probable it is that B is true and vice versa. Let me give you guys an example where this works and an example where it doesn't work because the statements aren't independent. A equals, let's say we're flipping a coin. A equals flip 1 is heads. B equals flip 2 is heads. What's the probability that both flips come up heads? Probability A and B, right? Well, as I just drummed into your heads last lectures, I went on and on and on about coin flips are independent. So we can use this multiplication rule, right? 1/2 times 1/2 equals 1/4. Probability of A and B, right? It works fine here because these are independent. Don't use this for dependent propositions, though. If you do, you'll end up with stupid answers. Let's say, World Series already happened, so we know who won, but let's say, it hadn't happened, and you're asking me what I thought the chances of each team were, right? I think the Braves have a little bit better chance, so I'd say, well, the probability that the Braves win the World Series, or A here, is 3/5, 60%. What is the probability that the Astros win the World Series? Well, 2/5, 40%, right? Well, what's the probability of A and B? Well, we multiply 3/5 by 2/5, and we end up with 6/25 or 24%. But probability of A and B literally says, what's the probability that both the Braves win the World Series and the Astros win the World Series? That's stupid, right? There is literally zero chance that both of them win. And here we get 24%. That's just crazy. That's dumb. Obviously, we've done something wrong. And what we've done wrong is these are dependent statements. If you know the Braves won the World Series, remember, dependent means if you know that one statement's true, it tells you something about the chances the other statement's true. Well, if you know the Braves won the World Series, it tells you a lot about how likely it was that the Astros won. It tells you literally that the Astros have had zero chance of winning. There is zero chance that they won because they both can't win. If you knew the Astros won, you would know that the chances the Braves won is also zero, right? If you knew the Astros lost, you would know the chances the Braves won is 100%. A and B are dependent, so you can't use the multiplication rule, or you will get blatantly stupid answers like 24% chance both teams won the World Series, right? That's crazy. That's dumb. That happens because we are using the multiplication rule, which only works for independent propositions, independent statements, for dependent ones. Weisberg has an example using the weather, but, use one with baseball teams. More examples are always better. So the addition rule tells us that the probability that A or B equals the probability of A plus the probability that B. But again, we have to keep one restriction in mind. This only works if A and B are mutually exclusive. Mutually exclusive means that whenever A is true, B is false, and vice versa. If you want to use like our little circles we were using before, all of these, in these cases, there's at least this one little slice here in the middle where both A and B are true. A and B overlap. There are some cases where both are true. Mutually exclusive propositions, there is no overlap. They look like this, right? There's no place where A and B touch. They can't both possibly be true. If one is true, the other is not, and vice versa. Here's an example of a mutually exclusive propositions, a case where this addition rule works. What's the probability the Mets win the World Series in 2022? A equals Mets win World Series in 2022. B equals Yankees win World Series in 2022. Probability that A equals probability that Yankees win. Sorry, Mets win. Probability that B equals probability that Mets win, right? Sorry, I keep mixing this up. A equals Mets, B equals Yankees, right? I really have no idea what their chances are. I don't follow baseball as closely as I used to. Other stuff gets in the way, right? But let's just say I think there's a 1 in 20 or, same thing, 5 in 100, 5% chance the Mets win. I think there's a 10% chance, 10 in 100 chance the Yankees win. Well, look, these are mutually exclusive, right? If the Mets win the World Series, the Yankees can't. The Yankees win the World Series, the Mets can't, right? These two events, A, maybe Yankees win, B, Mets win, no overlap whatsoever, so we can use the addition rule. Probability A or B equals probability of A plus probability that B equals 5 100ths plus 10 100ths equals 15 100ths or 5%. Sorry, 15%, right? But let's try it with let's try it with some statements that are not mutually exclusive, right? Joe Biden will be elected president in 2024 is A. B is the person elected president in 2024 will be a man. So probability that A, I mean, I don't know, right? Biden's old, he might die, his popularity is pretty low right now. On the other hand, he says he's going to run again. Incumbents tend to win. You know, so well, let's just say 40%, right? You know, I'm pulling the number out of thin air, but that's roughly what I would peg it at right now, to be honest. Person elected president in 2024 will be a man. Like it or not, I think this is probably true, right? Biden will probably run again. If he does, he'll almost certainly be the Democratic nominee. I think Trump is the most likely Republican nominee again. They're both men. You know, even if it's somebody else, there's still a chance it'll be a man. I might even put this higher, to be honest. But let's just say 70% chance the person elected in 2024 will be a man. So what's the probability that Joe Biden will be elected president or the person elected president will be a man? Well, we try to do our little addition formula. 4/10 plus 7/10 equals 11/10 equals 110%. Like, that's even more obviously stupid than the last one, right? There can't be a 110% chance because the next president will be a man, because there can't be a 110% chance of anything, right? That's just nonsense. Despite what those stupid antiperspirant ads, you know, deodorant ads when I was a kid used to say, just a nonsense expression. Well, what we've done wrong here is that these are not mutually exclusive propositions. In fact, they actually look like this, right? B's bigger, you know, but look, A, the person elected will be a man, actually completely encompasses Joe Biden will win, right? If Joe Biden wins, a man is one. That's not the only way a man could win. Trump wins, a man is one. Marco Rubio wins, so on and so forth, right? Well, what happens? Well, we count B once when we count A. Then we come back and count B again, right? We've already counted B because B's inside A. When we count A, we automatically count B, but now we make the mistake of counting B twice. You know, when they don't overlap like this, when we count A, we don't touch B. When we count B, we don't touch A. We don't do that double counting. But when they overlap, when they're not mutually exclusive, we double count. When we double count, we end up with dumb answers, like 110%. Now, if you wondered last time, from the addition formula, you can also get that the probability of A or not A is 100%. You know, right? Think about it this way. A or not A are mutually exclusive, right? If A happens, not A can't happen. These are certainly mutually exclusive. So probability of A or not A equals probability of A plus probability that not A. And remember, the probability of not A equals 1 minus probability of A. We do some super simple math. Probability not A plus probability of A equals 1. This statement, A or not A, is always true. In inductive logic and deductive, you know, they call this a tautology. It's just always by definition true. All right. Now look. Both of these ways of figuring will tell us what these are. Probability of A and B, probability of A or B in some cases, but we have some real strict limits on it, right? How do we figure out what A and B is when the two statements are not, how do we figure out what A and B is when they're not independent? how do we figure out what A or B is when they're not mutually exclusive? Ways to do this, things get a little more complicated. We will talk about this in coming weeks, but next time I want to talk about this idea of conditional probability. All right, so that's it for now. Next time, conditional probability, where we'll start to get into some really important ideas.